Good morning, everybody. So my talk today is about SSR technology for scalable real-time applications. So there are several co-authors of the same kind and myself who did the presentation. So this is the outline. So I will roughly talk about the differences between GNSS Augmentation, SSR, and OSR domain. I want to elaborate a little bit the advantages and benefits of SSR technology for real-time services. And this will lead into some benefits, that it is very scalable to use the SSR technology. Then I will briefly talk about SSR standardization. I can only pick up two issues from the standardization. And finally, I want to give a summary and outlook. So first, GNSS augmentation in SSR and OSR domain. So I think everybody recalls the simple GNS or DGPS approach, where you have a known reference station and you have the coordinates of the satellites, and from this you can determine the lump sum of all GNSS errors. And these range errors are then transferred to a user, and he can apply it to his measurements and improve his position capabilities. And since this actually is using observations directly, this is termed generally observation space representation, or OSR. So example for these are RTK in the classical sense, network RTK, where you use network of stations, DGPS. So this is what commonly is applied in real-time application today. So on the other hand, we have GNSS augmentation in the SSR domain. Here we try to decorrelate every error component and estimate every error component separately. So we want to distinguish or separate satellite clocks, satellite orbits, satellite signal biases, ionosphere delay and advances, tropospheric delay. And the user then can, with these individual corrections, compute for his own position correction for his observations, which gives him a better positioning capability. In addition, SSR can provide accuracy information on these GNS correction. And as you see, as we are talking about Statespace and GNSS errors, this is termed commonly Statespace representation, or SSR. So examples are SBus, for instance, the PPP, commonly used, and PPP RTK with a very high accuracy attempt. So scalable services with SSR. So what are the benefits? So what we have is we need to bring the corrections to the users. And in this sense, we have to look at the communication link. And the classical approach in the observation space is, probably you know the term, is a pseudo-reference or a virtual reference station data you transmit to the user and he applies it. And for this task you need a duplex channel. So you have to talk with the server to send your position and get the individualized corrections. On the other hand, SSR is completely a broadcast capable service. So you determine the state space representation, the state space, the GNSS errors, transmit them, and the user, for his own position, can compute the correction. So this is a major difference, that you are broadcast capable. And this opens a lot of communication channels to use. So besides the internet, the common media, you can use satellites, digital radio, and so forth. Another feature of state-space technology is the bandwidth issue. So if you have a look at the individual characteristics of each GNSS error components, you have the options to reduce the bandwidth. So in the upper picture here, this is a classical case. Every error is transmitted as a lump sum, for instance, with the same rate to the user. There is no separation between individual components. But if you look at the characteristic of each error component, you will very quickly see that the clock is the most frequently changing error component, and that other are slowly changing, and you can use these different characteristics to reduce the bandwidth. You see this in this graphic. We have the clock corrections at a high rate, but then you can transport ionosphere, troposphere biases at a very low rate. And this reduces the bandwidth very, very significantly. So this is an essential feature of SSR. Furthermore, a scaling in signals. I put here one example for GPS. You have already clocks, orbit, correction messages, signal biases, ionosphere, troposphere. So you can easily add now new signals. For instance, in this case, L5 can be added when you additionally transmit biases, satellite biases for the signal. And other components like the troposphere, ionosphere are basically the same, frequency dependent in some parts, but are basically the same for all GNSS. So this is very scalable in the signals you can support with the technology. It is also a feature that you do not need to have the same hardware on every reference station. This is depicted in this graph. You have some L5 capable stations, but most of the stations are L1, L2, for instance, just as an example. But you can derive the state space parameters from a few set of reference stations. For instance, even if you think of Galileo, then you need only a subset of stations which supports Galileo, but you can determine the state for every GNSS. In addition, SSR can be scalable also. You can provide this in the same stream information for single frequency user for the mass market, but also in addition high precise information for the high precision geodetic users. Another point is scalability in the area, in the region. So we can set up easily services which have a very high accurate position capability within the network, depicted here on the island. And outside, in the neighboring region, you just use, for instance, for PPP, the clock, orbit, and bias information. And only the ionosphere and troposphere is optimized and transmitted or provided for the area where you can do the high accurate positioning. So very important is also that SSR technology is backwards compatible. So you always has the option to convert SSR data back to classical observation space data. So you convert SSR data back into RTCM, back into RINEX data. So you can feed it easily into existing legacy algorithm. So this is depicted here. We have the classical case, the observation space domain with a dual communication channel, and we call it an OSR rover. And then you have SSR, and then you can do the conversion SSR to OSR at the server. In this case, you need the communication link to do twice, dual communication link. Or, sorry, no, working so. Or you can do it at the rover side, the conversion. Or in the future, you will directly apply the correction. This is somehow a little bit a paradigm change in thinking, but at the moment, the most feasible way is that you convert SSR back to OSR and feed it actually to your algorithm, which are already there on the rover. Okay, next topic is standardization. So since 2007, we already working in a RTCM Special Committee 104 working group on developing standards and messages to transmit all these information from the Statespace. The goals are in the RTCM SSR development that we develop messages that are self-contained, flexible, suit every application, and should be non-restricted to anybody. So we avoid to focus on one individual approach or methodology or model, and we want to be very flexible and free in this. And the point is we want to use this scalability of SSR, so it should support every GNSS application with different accuracy requirements. So what we achieved so far is we standardized already orbits, clocks, and code biases and user range accuracy, but only for GPS and GLONASS. We proposed already phase biases, vertical tag message since 2013, but it's a little bit lacking in the acceptance phase of the RTCM working group. And we are already preparing and working on concept, but also implementation for slant tag. Slant tag means individual receiver, satellite-dependent ionosphere, troposphere, and additionally compression of these messages. But generally, at the moment, the work and the progress is slowing down at the RTCM because of a new interoperability working group which has been established. But in the future, we see most probably that if we have the complete set of messages, then acceptance in between the working group and the RTCM will be possible. So here are now some features of the RTCM standardization. Satellite biases, you know, every signal transmitted by a satellite experience some delays in hardware and software of the satellite. Therefore, we introduced satellite biases as absolute biases. We put it here in quotations because there might be a remaining effect due to averaging, reference receiver bias, and so on. We heard another expression for pseudo biases. So basically, absolute biases for code and phase signals. And this also supports relative concepts of biases. And it is expected and has also been demonstrated that all existing other bias concepts, software-dependent bias concepts, can be mapped to this approach. So up to now, this has been testified and demonstrated already. Another point to mention is we split some state space information into different messages. For instance, I depicted here the ionosphere. The ionosphere, you see here, ocean area, continental area. We firstly introduce a spherical harmonic model. This is the gray line here. Then we add a global slant tag, we call it. This is associated to the satellite, moving with the satellite. This is supporting, for instance, the ocean area. Then you have, for the continental area, a regional S-tag model, which is supporting higher precision for continental region. And the last one is a gridded information for this area where you get the highest precision. So we are splitting this information over several messages, and with every message, you add these messages, and every adding of message gives you more accuracy. So this is also a feature of scalability of SSR. Summary outlook. So I talked a little bit on the benefits and advantages. So SSR technology is a broadcast correction service. It can minimize bandwidth. It's very scalable with respect to different GNSS, the variety we are facing in the next years. variety of signals. It is scalable in positioning accuracy. It's scalable in areas. And one important feature is it is also backwards compatible. So we see state-based representation as the most convincing technology for GNSS augmentation technology to cope with the increase of signals and new constellation. We are facing a little bit, I termed it here, a challenging status to standardize this. It's very difficult in an industrial consortium to standardize these information, and so the scientific community is very important to verify and testify these approaches and confirm the industry that this is the right path. SSR technology will probably substitute the conventional OSR techniques in the near future, and this is the reason why we are working on this technology. And this is a fusion, the future. We think that the global application, PPP application, IGS products, and the local application can be merged, a fusion of this technology for high precision application in real time for scalable services. So thanks for your attention.
Thank you very much. I think there's time for one quick question.
Yeah, do you have any test implementation of this technology?
Yes, definitely. So, for instance, you know the QZSS system, and the QZSS system is transmitting SSR information over the L6 channel, and this is properly working. Oh. So again, the QZSS system, for instance, uses the L6 signal to transmit SSR corrections for complete Japan, and this is completely perfectly working, yes.
Thank you. I think we should proceed to the next presentation, which is given by Simon Bonville on real-time clock combination supporting precise point positioning with ambiguity resolution. Do that now?
If you, I don't know, but I can improvise. If you minimize this one.
No idea how it is. Okay. It's this one.
Yeah. Great.
Okay.
Thank you.